Hello and welcome. In the last two videos for Chapter 2, we have talked about what a derivative is and how to find the derivative using limits, whether we're finding the derivative at a particular value or we're finding the derivative as a function. But there is a much more efficient way to find derivatives that you can actually sort of see from patterns forming using those limit properties. But what we're going to do in this lesson is we are going to summarize those properties. So the first property we're going to talk about is the power rule. So if you have an expression, a variable to an exponent, what you're going to do is you're going to take the exponent and you're going to drop it down in front to make it the scalar in front of the exponent, and you're going to decrease the power by 1. So here on number 1, the power that I have up here is 4, so I'm going to drop that down in front. I'm going to keep my x the same, and I'm going to take that exponent that was a 4 and decrease it by 1 to get 3. So the derivative of f of x equals x to the 4th is f prime of x equals 4x to the 3rd. And if you tested this out using limits, you would get the exact same answer. The second property that we're going to identify, or the second derivative rule, is that if you take the derivative of a constant, you get 0. So in this case right here, if I was taking the derivative of just 200, that would give me 0. But we're going to come back and work on number 2 in just a minute. The third property is the scalar, or the multiple rule, which says if we have a number in front of a function or being multiplied by a function, we can take the derivative of the function and then put that scalar back in front, or multiply the scalar afterwards. And then the last one, and there's a typo here, this should just be 1. Here, this should just be g prime of x, not g double prime. The sum rule says that if we have multiple functions being added together, we can find the derivative of their individual terms and add those together, or we can find the derivative and subtract them depending on what's going on. So if we look at number 2, we have a couple of things going on. We are going to find dy dx, or you could say y prime. So the first thing I'm going to do is I have two terms. So I'm going to find, term 1, term 2. I'm going to find the derivative of each individual term and then keep the addition symbol in between them. So our first term, we're going to apply the power rule. So that's going to be negative 2/3 times x. And it's going to be to the power of whatever negative 2/3 minus 1 is, because I should be taking my exponent that was already there and subtracting 1. Well, negative 2/3 minus 1, which is the same thing as 3/3, that would give me negative 5/3. So this is going to be to the power of negative 5 over 3. If I take the derivative of a constant, I get 0. So I guess I could clean this up a little bit. dy dx equals negative 2/3 x to the negative 5/3. And you can go ahead and leave that as a negative exponent. You don't need to rewrite it using positive exponents. For number 3, we are going to look at each individual derivative. So the derivative of this constant 5 is going to be 0. And I want to remind you that if you have negative 1 over 2t to the 3rd, this is really the same thing as saying negative 1/2 times t to the power of negative 3. So let's actually rewrite h of t here. H of t equals 5 minus 1/2 t to the negative 3rd power. Here's why this is helpful. Now it's easier to see how to apply the power rule. So we already said the derivative of this constant is going to be 0. Now I'm going to drop my negative 3 down. Negative 3 times negative 1/2 is going to be positive 3 over 2 times t. And then my exponent was negative 3. I'm going to subtract 1, so that's going to give me negative 4. Why don't you go ahead and rewrite number 4 so that this first piece has a negative exponent, and then go ahead and take the derivative on number 4 and then unpause the video and see how you did. So hopefully you have had time. I'm going to move down here a little bit. I'm going to rewrite f of x as 5x to the negative second plus 3x squared. If I drop the negative 2 down, let's use some more space down here. F prime of x is going to be, if I drop the negative 2 down, negative 2 times 5 is negative 10x, and then if I decrease that exponent by 1, I get negative 3. If I drop the 2 down from 3x squared, I get 6. 3 times 2 is 6, x to the first power. And here is my derivative. So the power rule, we drop that exponent in front. If there's already something there, we multiply our exponent by whatever was there, and then we decrease the exponent by 1. The derivative of a constant is 0. If there is a scalar or a multiple in front, you can just continue to multiply that, as we just did over here when this 5 in front became a negative 10. And then lastly, we can break each sort of polynomial or each term into different pieces and take the derivative of each term. Let's look at some more examples. So here on number 5, it is asking us to find the rate of change for each situation. So the rate of change for part A, it's asking us to find f prime of x, meaning find the derivative. Well, if I drop my exponent down using the power rule, I get 2x. The derivative of 5 is going to go to 0. So f prime of x is 2x, which means I could evaluate the derivative for f at any value of x by simply plugging it into this equation. For part B, they're going to ask us to evaluate it when x is 3. So I can substitute 3 in to get 6. F prime of 3 is 6. The derivative evaluated when x is 3 is 6. Part C, this notation is just asking us to find the plain old slope. No derivative work, just the slope. So what that means is we need to find f of 11 minus f of 3 and divide that by 11 minus 3. Well, f of 11, so I'm plugging these numbers in up here. 11 squared is 121 minus 5 is going to be 116. If I plug 3 in, 3 squared is 9 minus 5 is 4. And we're going to divide that all by 8. And if I do 116 minus 4, I get 112. And 112 divided by 8 is 14. So the slope, or the average rate of change over that interval in number 5 is 14. Okay, let's look at number 6. Something that I find helpful is to, anytime I see a radical, to rewrite it as a rational exponent. The reason this is helpful is because now it's easier for me to see how the power rule applies. I'm going to drop that 1/2 in front. If I subtract 1, 1/2 minus 1, I'm going to get negative 1/2. So there's my derivative. I wouldn't recommend rewriting this until you actually need to use it for something. So I'm going to rewrite it actually off to the side because we will, in part B, need to plug a number in there. So this is the same thing as 1 over 2 times the square root of x. Because I can make that exponent positive by putting it in the bottom of the fraction, and 1/2 is the same thing as the square root of x. So now for part B, we're going to plug in 4. So 1 over 2 times the square root of 4, which is going to be 1 over 4, 1 over 2 times 2. Part C is asking us, again, just to find the slope between 4 and 9. So f of 9 minus f of 4 over 9 minus 4. The denominator is going to be 5. The square root of 9 is 3. The square root of 4 is 2. This is going to be 1/5. The average rate of change between 4 and 9 is 1 over 5. I encourage you to pause the video and work through 7 and 8 on your own. And I'm going to clear out some space for us to see them a little better. Here we go. For number 7, I'm going to rewrite this as 2x to the negative second. Again, it just makes it easier for me to use the power rule here. So I'm going to drop this 2 in front. 2 times the negative 2 is going to give me 4x. And if I subtract 1 from that exponent, I'm going to get negative 3. This could also be written as negative 4 over x to the third power. The only time it's helpful to do this is if we have something like part B. So I'm actually going to plug that in now. Negative 4 over 1/2 to the third, which is the same thing as negative 4 divided by 1/2 to the third is the same thing as 1/8. And I'm using this old school division so we remember that we can flip and multiply. And this is going to give me 32. So f prime of 1/2 is equal to 32. But not positive 32. Where did my negative sign go? Negative 32. Okay, for number 8, and hopefully you had time to try this one on your own, if we apply the power rule, we're going to drop the 1 down and decrease our x. So the derivative of 3x is just 3, because x is already to the first power. So if I decrease that by 1, I get x to the power of 0, which is just 1. And if I take the derivative of this constant, I just get 0. So the derivative of 3x minus 5 is just 3. Well, that should make sense because this is a line, and what is the derivative? The derivative is the slope. The slope is 3. Part B is asking us for f prime of 100. Well, what did we just say? We said no matter where we are, the slope is 3. So I could ask you for f prime of 1,000,000 or 100,000. That is also going to be 3. I could ask you for f prime of -2. That is going to be 3 because for this function, which is a line, the slope everywhere, no matter the x value, is going to be the same. And that slope is 3. Now that we've gotten comfortable with finding the derivative using these basic rules for differentiation, let's go ahead and apply this back to the idea of a tangent line and to build on some of the concepts we've already been looking at. So determine the equation of each tangent line through the given point on f of x. So in order to write the equation of a line, we need two things. We need a point, which we have, and we need a slope. So before I even find my slope, I know that I can write out everything except for the slope using point slope form. So what I need is to figure out what my slope is to fill in this part of my line, of the equation of the line. How do I find the slope? Well, first I need to find the derivative. So I'm going to drop the 2 down. That's going to give me 2x plus the derivative of 3x is just 3. The derivative of 5 is 0. This function, the derivative as a function, gives me the slope at any point in time. For this problem, we care specifically about the slope when x is equal to 2. So we're going to plug 2 into our derivative function. 2 times 2 plus 3 is going to give us 7, and that's what's going to go here. So here is the equation of my line. Why don't you go ahead and pause the video and work through number 10 on your own. So here is my derivative. We're going to evaluate that when x equals 2. So 4 times 2 to the third plus 3 times 2 squared minus 4 times 2. This is going to give me 32 plus 12, 3 times 2 squared minus 8. That's going to give me that my slope at this value is going to be 36. F prime of 2 equals 36. So we have our slope. Y minus the y value, wait a second, we don't have a y value yet. That's okay, we can find it, equals our slope, 36 times x minus the x value. How do we find the y value? Well, we just plug in 2 into our original function. That'll tell us what the output is there. So that's going to give us 2 to the 4th plus 2 to the 3rd minus 2 times 2 squared minus 1. And if we simplify that out, and since I don't have room, I'm not going to show those steps there, that's going to give us 15. So f of 2 is 15. If I plug 2 into the original function, and that gives me this y value that I need for our tangent line. So pause the video to make sure you understand those two, and I'm going to clear some space for us to do 11 and 12, and then we're going to recap what we have covered in this video. Number 11 says, determine the x values that make the following true. We are being asked when we have a horizontal tangent. A horizontal tangent would look like this. What is the slope of a line right there? The slope is 0. So what we're looking for is when is our derivative equal to 0. So the first thing we need to do is find our derivative. Well, if I drop this down, I get 3x squared. If I drop this down, I get minus 6x, and that derivative goes to 0. And now I can just set this derivative equal to 0. If I want to solve this, I notice that I have a greatest common factor here of 3x, and if I factor that out, I get 3x times x minus 2. So I want to know, where is 3x 0? Well, that's true when x is 0. Where is x minus 2, 0? That's true when x equals 2. So the answer to this question is when x equals 0 or 2. That is when we have a horizontal tangent. Number 12 says, here's our function. Tell us when the slope is 18. So you're going to find the derivative and set it equal to 18. Why don't you go ahead and pause the video and do that on your own? So hopefully you had time to work through that. There's my derivative. Now I'm going to set my derivative equal to 18 because it's asking us when the slope is 18, and the derivative is the slope. And now I'm going to solve for x, and that's going to give me that x is plus or minus 2. When x is 2 or negative 2, the derivative of this function, or the slope of this function, is positive and negative 2. Sorry, the slope of this function is 18. So let's recap what we've covered in this video. We talked about the power rule, the constant rule, the scalar rule, and the sum rule, are basic rules for differentiation. Then we did some practice with using those rules for derivative. We recapped a little bit on how to find just delta y delta x, or the slope. We reminded ourselves that the derivative is the slope. And we wrapped up by tying this back to finding equations of lines, or finding when a derivative is a particular value in these last two examples. So go ahead and write down any questions you have, and I look forward to supporting you on this in class. Thanks for listening.